Here we go. You don't seem that upset with me, so that means you probably didn't go on Moodle in the past, I don't know, half hour.
No, I'm kind of upset.
I know, I shouldn't have set you up like that.
I didn't understand.
I
At all.
posted a number of assignments. What? I know. Rude. The binomial distribution, which we're doing today, okay, and an Excel assignment. But you'll be happy to know that the Excel assignment might make that other assignment easier because you don't have to do the calculations by hand. So maybe, I don't know, try the Excel assignment first, or it's up to you. And then it's only because I split out the normal approximation to the binomial. We'll do them both today, so you'll be able to do them both assignment 7 and assignment 8. Okay. They are on test 1 on Tuesday. Okay. They're not due until the 16th, so, but probably do them before Tuesday if you can. Okay. And where was I here? Excel, I don't have a pointer on here. So the Excel assignment for the binomial just might help you out. Okay. In terms of finishing the binomial distribution, there is a question on here that I'll pull up. I renumbered the assignment, so it says assignment 10, but it's not. Where you can, we haven't done it yet, so this isn't going to make sense, but you can do it by hand if you want to, or you're also allowed to just use Excel, and it's a lot quicker, right? And so you're allowed to use Excel if you want to. But that example is posted for you. I also posted a link to the normal approximation to the binomial. It's just a little shorty, just in case we don't quite have time to get through it properly today. I think we will, but you never know. After that, these things are not on the test. Okay, the assignment 9 is not on the test. In fact, it'll never be tested. The poisson, fun to say, fun to do. Yeah, fish. I think it's a last name in this case, probably some statistician sometime. But the Poisson distribution is another distribution, and what I have prepared for you today for the Poisson is a video assignment, and so at least one person got my Food Network reference. The dish I've prepared for you today. So the video assignment is linked to a video, and you watch a little snippet, and then it'll pause and get you to answer a question, right? Kind of an assignment question, and then you get to keep watching the video, and then it'll pause and get you to answer the question, and so on. There's also an Excel assignment for the Poisson. Again, not tested. And a bonus assignment in case you're really feeling like, wow, I just can't get enough of this stuff. But anything on a bonus assignment is not tested. All right, so it's just to boost your assignment grades. Okay. I know, overload, and I apologize. But it's really only, shouldn't say only, 3 assignments on the test. 2 if you don't count the Excel one. It's pretty good. Getting there. Okay. We're going to refer, any questions before we start? I wanted to warn you, because we have a full class, even though, well, it feels pretty full still, but it'll be really full on the test day, okay? And so I'm going to do assigned seating. Okay? So you won't be, probably won't be in your regular spot. Okay. And so you'll come in and look for your name on the desk, and that's the test that you write. Okay. And so that's because I don't know your names yet, and I like to know where people were sitting and stuff like that. And so so just be prepared, assign seating for the test. So because I always had a hard time when I had to sit in a different spot. I know. But I think that's pretty common. Okay? So just be prepared for that. Okay? Good. I remembered to say that. Anything else? Any questions? Yeah. Good. I feel like yes. Okay, good. There. It's all in there. Thank you. Any other questions? Good. All right. So we introduced the Milgram experiment last day, which was only on Tuesday, so it feels like mere moments ago, where we were measuring the willingness of study participants to obey an authority figure who instructed them to shock a learner if they answered a question incorrectly, and then we were really studying whether they refused to shock or whether they went ahead and administered the shock. And so Milgram found that about 65% of people would obey authority and give a shock, which makes the probability of someone, a randomly selected person, administering a shock is 0.65. We're going to use this probability today, so that's why I wanted to bring it in here. And kind of crazy, there's been more research done on this, and they find that this 65% stays pretty steady across communities and time. So that's kind of wild. We've seen the normal distribution. Now it's time for our second distribution, the binomial distribution, or I guess third if you count the geometric, which we saw last day, right? But the binomial is on test number 1. Okay? In fact, it's going to be 4 marks with 2 bonus marks. I like to make them bonus marks, but I'll highlight what's what later on as we come upon them. Okay. So a total of 6 marks. You can boost your grade by 2 marks. That's nice. When the total, I think, only worked out to be 28. So 2 bonus marks is pretty good. Suppose we randomly select. Oh, they changed their mind. Oh. Let me mime my way through it. Anyways, I don't think they want it in here anyways. So if we select 4 individuals, hey, to participate in the experiment, what's the probability that exactly one of them will refuse to administer the shock? And so we know how to solve something like this. Right? We already kind of, I mean, maybe not off the top of your head, but if you had to sit down and try to solve this, what's one way that you could solve this problem? You could use a tree, right? That might be nice. Okay. So we can call these people Alan, Brittany, A, B, C, D. And what we can do is we can think about it as a tree where the first set of branches might be Alan, the first teacher that comes into the room. And so here we have Alan, and we're talking about refusing to administer the shock. Okay? And so let's use a refusal to shock and the complement of that, which is to shock, but it's always nice if we can boil it down to just the complement. Yeah? Now they refuse to shock with a 0.35 probability, okay, because the probability of shocking was 0.65 from earlier. Okay. Okay. So now Alan either refused or he went ahead and administered the shock. Now we move on to Brittany. Now Brittany still only has two choices, but depending on what Alan did, right, that'll be a new set of branches. Now these probabilities stay the same. We're used to the probabilities adjusting, right? Conditional probabilities for trees, but you can still use them for independent probabilities, which we have here. 0.35, 0.65. And then we have Caroline. 1, 2, 3. I need to make it not as wide, I guess. So here we've got C, and then finally 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Got a little wonky there. We're here, we have Damien. Huh? I won't map out all the probabilities, but oops, as I say that I do. But whether they refuse or not might be nice. Refuse, 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 and then not. I don't know why that felt easier. It's probably not. Can see it gets a little messy here. But you could solve this with a tree, right? If you wanted to. Luckily, we're not going to have to do that. Imagine if we had something very reasonable, like maybe we had 10 teachers instead of 4. What would that look like? You'd have to have 10 layers in your tree. So even though there's only 2 possible outcomes for each of them, it gets kind of out of hand pretty quickly, right? And so, yes, you can use a tree, of course, but we'll have a better method, or an easier method, I should say. Okay. So exactly one shock. Well, Alan maybe does, exactly one refusal. Alan refuses, which if we're forcing exactly one refusal, right, that's the end of our options. Okay? Whereas if Brittany is the one who refuses, that means Alan shocked, Brittany refused, and then the rest of them went ahead and did the shock. Right? If Caroline is the one who is refusing, that means that I've got a shock and a refusal and then another shock. And then finally, if Damien is the one who gives the shock, that would be this tree here. It doesn't matter which order you organize the refusal and the shocks, right? You're going to have 1 refusal and 3 shocks. So once you multiply those things, right, you'll get the same number at the end of each of these branches, right, that we're interested in. The important part is, though, that we've got 4 different branches that satisfy this criteria, right? And so this first branch or this second branch, or this third branch, or the fourth branch. When we're saying or, right, that means we have to add the probabilities, right? Add the probabilities at the end of each of these branches. Yeah? So we're going to have a formula that just does that for us, right? But the formula looks a little crazy if you haven't kind of seen what's going on in the background beforehand. Yeah? So we could have mapped out the possibilities with our slots instead, right? So we've got our different scenarios where we get the first refusal and then followed by 3 shocks, right? It's the same as that first set of branches that we looked at, right? And we would find that the probability at the end of the branch would be 0.0961. Yeah? And notice it doesn't matter where the refusal is. It's already highlighted in pink, but still, right? The probability stays the same here. That's nice, right? So we would find, right, that we would add up each of these probabilities, which we can summarize as 4 times 0.0961. Right? That's the same as each of these being added up 4 times, right? And so here, 4 is the number of ways of exact, or yeah, I'll keep going, of exactly 1 refusal, right? Different combinations. Huh? So like I said, we'll have a formula, most importantly, to find this 4, right? Because that's the hard thing, right? Is figuring out, well, how many ways can I have exactly 1 in 4 trials, right? If you only have 4 trials, right, from last day, the trials would be the number of teachers, right? So we had A, B, C, D. And so we're going to start really calling those trials. Now, how you're going to think about trials is those are times that you try to get a success, right? Whatever you've defined a success to be. The binomial distribution does just that. Okay? So we wanted the probability of a given number of successes, which we're going to denote with a lowercase k. Okay? And so here, k, and I like to do a script k. I don't know why. It's just math, I think. K is going to be the number of successes. Okay? If you've defined a success as someone refusing to shock, right, then we wanted exactly 1 success in 4 trials, right? And so n is the number of trials. Oh. So we need to have these guys kind of locked down. I will say, so the k has to be the number of successes, okay? How many failures do you have then? If there's a total of n, then you must have n minus k failures, right? K successes, n minus k failures, the remainder are failures, right? And so therefore, there must be n minus k, which is the number of failures. Okay. Now, often students struggle with the successes because the successes can be fluid. It's whatever you're interested in. Okay? And so in the previous question, right, we wanted to know exactly one refusal, right? We could have rephrased that as exactly one shock, right? Now a shock is a success, right? So it depends on what we're interested in. Okay? And so here, the outcome of interest which I think on the practice test, which is why I use it for the practice, for the test, I should call it, it switches. So you have to kind of stay nimble, right? And that's just to highlight that, okay, well, it's the outcome of interest, okay, is your success. And just as before, P is the probability of success or of a success. And I use Q, which is really 1 minus P, which is going to be the probability of a failure. Oops. Failure. Sneak those in there from last day. Okay. We're building up to something. You can feel it. So what we found earlier, right? If the probabilities stay the same, probability of success and failure, and you're holding them fixed, right? 1 success and 3 failures, right? Then those probabilities, right, are all the same. The probability of a single scenario times the number of scenarios that can happen. Okay? This is the tricky part. Right? This is the tricky part. So the number of scenarios, we will have a less tedious way to figure this out. So let's just parking lot it for a little bit. I mean, in theory, you could make a tree diagram for all these scenarios, but it might get out of hand pretty quickly. All right. Think about bringing in 20 teachers. Now your tree has 20 layers. I don't want to draw that. Sounds terrible. Right? Even though 20 teachers is pretty reasonable for a study, right? Or subjects. The probability of a single scenario has to be P to the K, right? Because if we think about, oops, I went too far here. If we think about our 4 teachers here, right? We had 4 trials and I want exactly 1 success. So in this case, K is 1, okay? And N is 4. Okay? So I have 1 refusal followed by 3 shocks, right? 1 refusal here, it moved, but the result stays the same, right? And so I still have 1 refusal and 3 shocks, right? And 1 refusal and 3 shocks, and 1 refusal and 3 shocks. Right? So I can rearrange these. But what are we doing when we find this overall probability, right? We multiply these probabilities together. Okay? And so here, right, we have P is 0.35, K is 1, and N is 4 for this scenario. Okay. So I have P to the power of 1 times 1 minus P, or Q if you prefer, to the power of n minus k, and I should use k here, n minus k. That's going to be the same as 0.35 to the power of 1, because k is 1, times 0.65, the probability of failure, to the power of however many failures I need, right? N minus k, 4 minus 1 is 3. Right? It doesn't matter how those 0.65s scoot around the 0.35s, as long as there's only one 0.35, the result is the same, right? 0.0961. Right? I haven't checked it, assuming they did that right. So really what we're doing is each scenario can be summarized with, oops, sorry, I went too far, this formula here, p to the k, right? The probability of success to the power of however many successes I need, right? Times the probability of failure to the power of the number of failures that I need, right? So that brings us back here, right? The probability of a single scenario, I'll highlight it because we've talked about it a lot, has to be p to the k, right? P is the probability of success to the power of the number of successes, and then 1 minus p to the n minus k, right? It's the probability of failure to the power of however many failures you have. The binomial distribution describes the probability of having exactly k successes in n independent Bernoulli trials with a probability of success p. Now, if you take a sneak peek on your formula sheet, I forgot to bring spares, sorry. We'll have to make do. On the test, you'll get a fresh formula sheet and a fresh table, right? Because I can't be checking everyone's formula sheets and tables. Okay? So don't worry. If you forget yours, I've got them for you. In the binomial, and we're kind of ignoring this section for now. It's on, don't worry, it's coming up soon on the next slide. Okay, but the binomial probability, this is the part that we're picking apart right now, right? P to the k, probability of success to the number of successes, and then I use Q, just a little bit cleaner than 1 minus P, in my opinion, right? But I did define it down here. Q is the probability of failure to the number of failures, right? Now we need to work on this part, right? If you've seen the choose function before, right? This might look familiar. It looks like a fraction, but it's not, right? And that's what this section of the formula sheet is just meant to help you solve. Or you can use the choose button on your calculator. Might be nice. I'll show you how. So computing the number of scenarios is going to be important, right? Because we don't just want to consider one possible scenario. We have to consider all the possible ways that I could arrange exactly one refusal in 4 trials, right? Or if we kind of kick it up a notch, right? What if we have n is 9, right? That would be 9 layers in your tree. Yikes, already. Right, you need a big piece of paper, I guess. And K is 2 successes. Uh-oh, right. Yes, it's nice when the refusals are kind of lumped together, but they're also allowed to happen at any point, right? As long as there's only 2 refusals among the remaining 7 shocks, right? They're allowed to float around. And I just really don't want to do this with a tree to figure out how many ways I can rearrange 2 successes in 9 trials. Okay? You could, but I don't recommend it. Okay? And so here, notice that they don't even write them all out. Okay? To find the number of ways, and maybe I'll use k equals 2 just to emphasize. K equals 2 successes can be arranged in n equals 9 trials. We use the choose function. And I will go through, there's the mathy version down here, which I will go through, but I think it's more important that you know how to use your calculator for it. Okay? I would say any scientific calculator has some sort of choose function. Okay? And so choose function on your calculator often looks like something, what does mine look like? NCR, it's like NCR, or sometimes we have CNR, something like that. I don't think they'll use K, but where N is N, and R is K. Usually they use R, but K is special to the number of successes. Now I have, because I had to take a picture of my calculator the other day. I know, don't you hate it when that happens? You had to take a picture of your calculator. No, probably only happens to me. My NCR button is down here, so I'm going to copy this here. So it's often in the second function, so you have to use your shift to get there. Oops. And if you're having a hard time finding your choose button, I'm happy to help you after class. But you'll definitely want to have it unless you like doing some tedious math, which you can do as well. Okay. Now, I'm pretty sure on mine, and you'll have to play around with it, I have to put in my N first. Okay? And then hit the choose button, which is the shift and then the choose, right? NCR button. And then tell it how many successes I want. Okay? Whoops. To calculate the number of ways 2 successes can be rearranged in, I'll do K equals 2 successes in N equals 9 trials, which is from the previous slide. Okay. On my calculator, I would do the 9 button, copy, paste, 9. I'd have to go into my shift, my NCR, boy, tiny. No. Defeating the purpose. And then I would do 2. And then I think I have to do equals. Let me see. Equals. Well, I didn't leave myself enough room for that. Here she comes. Equals. But I think when your calculator doesn't do anything, you'd figure it out. I get an answer of 36. And you're allowed to write it. There's a couple of different ways that you can write it. You can write it using the shorthand of the calculator, right? 9C2 equals. So here, 9C2 is 36. You read that as 9 choose 2, right? How many ways can I choose 2 in 9 options? Okay. We can also write C9 2, or more commonly, we use this choose function, big brackets of n choose k, where we had 9 and I wanted to choose, 9 choose 2. Either way, the answer is 36. This is the notation on your formula sheet, right? And so you want to be really careful because that's not a fraction, right? 9 divided by 2 is not 36, right? And so often I'll see a little divisor in here because you can't resist. I know what you mean. Try not to do that, right? As long as you got the 36 and you didn't actually do 9 divided by 2, right? It's okay. I'm not going to penalize you. I'll circle it and say, don't do that. Right? But I know what you mean. Sometimes it's a force of habit, right? So as long as you've done the calculation correctly, I'm okay. But if you tell me 4.5, I'll have to dock marks because that's wrong, right? There's 36 ways. So this is the notation on the formula sheet. That's a lot easier than trying to figure out, okay, how many ways can I rearrange, and rearrange 2 successes in 9 trials, right? Covering all the different options. Yikes. Okay. So make sure you've got your choose function working. Should we do another one just for find? We'll do another. What if you have 20 trials? 22, 7. Wow. Imagine that tree. No thanks. All right. How many ways can you rearrange a series of 7 successes and therefore 13 failures in a layered tree of 20 layers? Whoa. Let's see. 20, choose 7. Well, there's 77,520 ways that you can do that. That's tough. What if you have to find something like 10, choose 3? This is just to make sure that you've got your calculator tamed, right? So that you're getting the same results that I am. 10, choose 3, I get 120. So make sure that you get those same results. Nice. That saves us some work, right? So now if I know how to find the number of scenarios that satisfy some criteria, and the probability of each scenario is the same, right? Then we've built the binomial formula. Yeah? And like I said, let's talk about the mathematical formula for the choose function, but it does involve the factorial, which I've heard through the grapevine they're not teaching anymore. Really, n? What's n factorial? N factorial. Let's start with 4 factorial. So that exclamation mark is as a factorial. Okay. 4 factorial would be 4 times 3 times 2 times 1. And so n factorial is n times n minus 1 times n minus 2, all the way through to 3 times 2 times 1. Tedious, but again, most calculators have a factorial button. Can I find mine? I don't know. I know it's on here, but where? Ha, I found it. It wasn't close, but here's my factorial button, x factorial. You won't need it. As long as you have mastered the choose function on your calculator, you don't need the factorial button, right? It's just if you wanted to. If you wanted to show off to your friends or maybe your parents over Thanksgiving. There you go. How's that for tempting? The choose function. N choose k, that's how we read this, right? And so you have n factorial divided by k factorial times n minus k factorial. There is a trick to working with factorials. And so if you have k as 1 and n is 4, that first example that we were working with, then 4 choose 1, mapping to n is 4 and k is 1, we get 4 factorial over 1 factorial times 4 minus 1 factorial, which is 3 factorial. You can write out all the numbers. 4 times 3 times 2 times 1 divided by 1 times 3 times 2 times 1. But because they're all multiplying, you're allowed to cancel those. So that's kind of the trick. And you're left with 4 over 1. So it's kind of fun to work with factorials. Same thing here. 9 choose 2. 9 factorial over 2 factorial times 7 factorial. Usually what you do is you just go till you reach a factorial that's in the bottom, right? 7 factorial is 7 times 6 times 5 times 4 times 3 times 2 times 1, but I'm about to cancel these anyways, so I just stop writing, right? So I'm left with 9 times 8, bless you, times 7 factorial, but that's divided by 7 factorial. So now I have 9 times 8 divided by 2 times 1. So it simplifies to 72 over 2, which is 36, which is what we found with our calculator. All right. So make sure for our calculator, we're not using R in this course, so, but Excel has a choose function if you prefer. Okay. So you don't need this stuff here as long as you've got your calculator under control. Yeah. Oh, before I do that, hang on. I do want to bring in the section from our formula sheet. I'll just do the whole thing, I guess. Here's a note on factorial notation. A mathematical fact is that 0 factorial is 1. Kind of interesting. Not needed for us, but might be nice to know. And we've got the choose function, right? N choose k, and this is the formula that we were working with mathematically, which I said you don't really need. And so here, that renders this whole section kind of useless to us. It's there for completeness, right? But, or use the choose function on your calculator. Which I would recommend. Right? It's there in case you want it, but I'm not expecting you to use it. We've seen this kind of notation before, right? How do we read this? X follows take a guess, a binomial distribution. Wow, instead of a normal distribution, we have a binomial distribution. And just like the normal distribution, we needed to know the shape, right, as the normal. And then we needed to know the mean and the standard deviation to describe the whole thing, right? In a similar way, we can describe the binomial distribution entirely with the number of trials and the probability of success, P. Yeah? And so these are what we call our parameters. Now, you're not really going to use this, but I think it's nice to see that there's shorthand for the binomial as well, although I don't use it. Okay? I do use the normal shorthand, but I don't use the binomial shorthand. This binomial probability, this is what we've been working up to, right? Now we can kind of look at this and feel okay, right? How do we read this? The probability that x equals k, okay, maybe just kind of squint that part, right, for now. But x is equal to k successes, okay? The probability of exactly k successes is how you could read that. So here, this you could read as exactly k successes. Is the number of ways that I can rearrange k successes in n trials, right? That's this n choose k function. Okay. And then we're back to, okay, the overall probability of each scenario will be the same, right? Probability of success to the number of successes times the probability of a failure to the number of failures, n minus k. Okay. And I will highlight this note that I am using this shorthand of Q. Q is the probability of failure, so Q is 1 minus P, but it is on there. And if you write 1 minus P instead of Q on the test, that's fine. I know what you mean. Right? I just prefer the shorthand for myself because I'm lazy. I'm saving 2 strokes. 2 strokes for every Q. That's pretty good. I know. You guys don't think like that. I do. Technically only 1 stroke since I write my Qs like that, but still. Oh, and then I'm saving this for a little bit later, but we will talk about that. Yeah. Maybe I'll make a note of that later today. So it's not that far off. It will happen today, but later today. Let's talk about the choose function. Which of the following is false? There are n ways of getting one success in n trials. Now, we saw that earlier, right, with the four teachers and the one refusal, right? And we ended up with 4 different ways of rearranging that, and that is true. Okay, so that will always be true. And what could you do? What can you do when you live in a shoe? You could prove it if you wanted to. If we remember this part, n choose 1 would boil down to n factorial over 1 factorial or times n minus 1 factorial. N factorial is the same as n times n minus 1 factorial. 1 factorial is 1 times n minus 1 factorial. The n minus 1 factorial go away. So it's n over 1, which is n. Though that is fun to do, it's not something I'm going to test you on, right? Because we just use our calculator, okay? And so I'm just going to go ahead and tell you that this next one is true. There's only, and you can try it with the formula, right? Try to rearrange it and kind of get comfortable with that. But again, it's not something that I'm going to test you on. So in the interest of time, which I'm scared to look at. Okay, I'm doing all right. Doing all right. There's only one way of getting n successes in n trials, right? That would be a refusal and a refusal and a refusal and a refusal, right? There's only one way to do that. You can kind of talk yourself into that. So that's true. And there's only one way of getting n failures in n trials. That would be the only scenario where I could make that happen is a shock and a shock and a shock and a shock, right? And so that's true. Oops. And you can confirm it, right, with the formula. The only one where I really want to confirm it for D is because it's not obvious to me. Okay? Well, it's obvious because the past 3 have been true, so this one must be false. But let's see what the answer should be instead. Okay? So for D, I want to find n, choose n minus 1. Which is going to be n factorial over k factorial, which is n minus 1 factorial, times n minus k factorial. Now n is n, minus k, which is n minus 1, yikes, factorial. Aren't I so nice to not make you do these on the test? So nice. I know. I'm going to simplify a little bit. N minus 1 factorial, I'll just leave it as is, but I suspect it'll be the one canceling with the top, right? So n minus n plus 1 puts me at n times n minus 1 factorial times n minus 1 factorial, and expanding this negative inside, right? N minus n is 0. Plus 1 factorial. And minus 1 factorial and minus 1 factorial. So I get n over 1, which is n. not n minus 1, making this false. Getting flexy with the factorials. It's okay. Don't let it clog your brain space, right? Any questions though before we? So binomial probabilities. If P represents the probability of success and 1 minus P, which I use a Q, represents the probability of failure, N represents the number of independent trials, and K represents the number of successes, right? Once we have those kind of figured out what they are for that specific question, then we can find the probability of K successes in N trials. In fact, I like to specify exactly K successes. What? In N trials. This is the same formula that's on your formula sheet, right? Here, this N choose K, use your calculator. I guess that's not super helpful. You're going to use your calculator for all of it, but don't use the formula, right? Q to the K, Q to the N minus K. Right. Nice. Hope we have an example. Not quite. Which of the following is not a condition that needs to be met for the binomial distribution to be applicable? I'm going to tell you because a lot of these are just factual. The trials must be independent. That has to be true. Okay. All of these have to be independent, right? Independent, identically distributed Bernoulli trials. The number of trials, N, must be fixed. It can't be changing, so of course it has to be fixed. We can't handle a changing number of trials. Each trial outcome must be classified as a success or a failure. That's what we established last day, and that's still true. The number of desired successes, K, must be greater than the number of trials. How? Can't be, right? K has to be less than the number of trials, right? Less than or equal to. So this little guy is false. Which means that the probability of success, P, must be the same for each trial, right? Since they're independent, that's implied. Okay. A 2012 Gallup survey suggests that 26.2% of Americans are obese. And obviously that's been defined at some point in this article, but we don't have it, so we just trust it. So among a random sample of 10 Americans, what's the probability that exactly 8 are obese? We need to figure out, we're not going to just do this, we're going to find what's the probability. We'll decide if it's pretty high or pretty low in a bit, once we have the probability. But what do we need? We need our N. That's a nice place to start. How many Americans am I selecting to see if they're obese or not? That's going to be 10. So N is the number of trials. K is the number of successes. Okay. In this case, if they are obese, that's considered a success in this scenario, in this question, right? which means that K must be 8. If someone being obese is a success, then P, which is always the probability of a success, must be 0.262, right? The probability of selecting someone who's obese. 0.262. And we can do our little math here. Q must be 1 minus 0.262, which saves us a smidge of work later on, I guess. 0.738. Once we have these 4 pieces, we're ready to put them together in our formula. And I was going to copy it, but the probability that X is equal to K, I'll use the version on our formula sheet, right? Uses the probability that X is equal to K is 10, or I'll do N choose K, the blank version first, times P to the K times Q to the N minus K. Now it's just a matter of plug and chug. So the probability that X equals 8, exactly 8 successes. I plug in where I see an N, I replace it with 10, and where I see a K, I replace it with 8. 0.262 to the power of 8 times 0.738 to the power of 10 minus 8. And if you wanted to jump straight to 2, that's fine. Let's tackle the 10 choose 8 first, right? Make sure that we all get the same value. So 10 choose 8, I get 45. So there's 45 ways to rearrange 8 successes in 10 trials. Usually the notation that I end up using is just P of 8, right? The probability of 8 successes, and I drop the X equals. Technically it's there, but it's not really doing anything. And so this is the shorthand notation that I tend to use. So 10 choose 8, we can replace it with 45. Now it's just a number. And let's see what we can do here. 45. And usually what happens is it's way too tedious to write out what these numbers are individually, and it doesn't really serve a purpose. Okay, so as long as you've written them out like this, and then you can just plow through and do your calculation, right? Making sure that you step down from your powers, depending on your calculator. Sometimes you have to tell it to step out of the power, right? So just play around with it and make sure that you get this times 0.262 to the power of 8. I have to step it down times 0.738 to the power of 2. Step it down. Couple of cautions. My calculator defaults to scientific notation, right? But you might remember you have to move the decimal. It's always going to be really, really small, usually, right? And so you have to move the decimal over to the right, or I guess to the left, technically. 1, 2, 3, 5, 4, 4, 1, 7, 1, 2, 1, 8, 5. Or on my calculator, it gives it as 5.44171218 times 10 to the negative 4. Right, yeah. Yeah, it's this 10 choose 8. So on your calculator, if you have the choose function, did you get it sorted?
So if we put down like the 10 to -4, would that be fine? Or do you want us to be further?
Nope, that's fine with me. Usually we need to add probabilities together, so then the decimal is nicer to work with. But no, if it's the final answer, scientific notation is fine. We'll go here, then here. Question? No, that was it.
No, yep.
Nice.
For like, in my calculator, it only, like, it doesn't do the scientific notation, but it does go all the way to the 171, the decimal place.
Oh, yeah. Yeah, that's fine. It's because this one's an engineering one and they think that these last few decimals matter. They don't. So that's fine. As much as your screen shows is good. Yeah. I will make a note here though, that it's going to be really important that you keep all your decimal places, or as many as you can. So binomial probabilities tend to be very small. They're still probabilities. They have to be between 0 and 1. Did you get it sorted? Sorry, I kind of left you there. Yeah. They tend to be very small, right? Still have to be between 0 and 1. Same rules apply, right? And if I consider all the possible outcomes, right, they should add to 1. But they tend to become kind of out of control pretty quickly for binomials. But they should all add to 1. And so binomial probabilities tend to be very small. So it is important to keep all decimal places. Usually, students ask me, how many decimal places do you want? And well, that depends. How small is your number? Right? If I was saying broad strokes, 2 decimal places, you would give me an answer of 0 here, and that doesn't tell me very much, right? So here, I kind of lose interest after the 7, for example. And so a lot of calculators kind of stop here-ish, right? And that's fine by me, right? And so I kind of tend to stop being interested at this point, but I want to hit a point where things are interesting, if that makes sense. So sometimes that's a lot of decimal places, and sometimes it's not a lot of decimal places. Right? And let me just confirm that I did my scientific notation properly here. You might recall 1, 2, 3, 4. Good, I did it. So this decimal had to move out, boom, 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 boom. 4 notches. I'm sure there's a way for me to change it out of scientific notation, but it's actually kind of nice sometimes. So make sure if your calculator gives scientific notation, you have to be able to recognize that. Sometimes it's really subtle, right? Sometimes there's just a space, -4 at the end, right? And so that can be really confusing. Many calculators give answers in scientific notation, such as 5.4417121185, I can't resist, times 10 to the -4. But sometimes this part is not as explicit, right? It can be an E -4, or the one I really don't like is just a space -4. That one's the hardest to kind of pick up on, right? And so here, right, there's just a tiny space followed by a -4. So be able to recognize scientific notation if it shows up on your calculator, right, is going to be really important. Another thing, it's a calculator heavy day, right? Keeping all the decimal places. I think we've talked about the store function, right? So a lot of calculators have a store function. Yeah. Because what if you wanted to know what's the probability of 8 or more being obese? What would you need to do then? That's 8 or 9 or 10, right? Because we only have 10. So you'd have to do this calculation 3 times and add them up. Oh boy. Are you going to make us do that? I will, actually. I know. Can you believe that? Tedious, but once you kind of get the hang of it, not hard. And so to keep all the decimal places, use your calculator's store function. Calculator's store function. And I say that with pretty good, pretty high confidence. Most scientific calculators have a store function. Okay? So on mine, I'll bring mine in again. Gotta crop it up. I have an STO button here, and above it, it says recall. I think the newer calculators, for some reason, they changed it so it says RCL with store above it. Yeah, I don't know why they would do that, but they did. And so just look for a store or a recall button. Okay. And depending on your calculator, there are different spots where you can store stuff. Okay. On my particular calculator, I am allowed to store stuff in A, B, C, D, E, or F. Okay. And so how I would store this number, let's say this number. Sometimes, or usually if I'm storing a number, I am storing it for later. And so I like to make a note to myself mostly that I stored this in, let's go crazy. I'm going to store it in C, right? Not just A, maybe. And sometimes you can store it in the number slots, or it depends on your calculator. But if you have a button that says STO or RCL, you have this capability and you just need to Google your way to it. But for me, I hit this STO button. So once I have this on the screen, I tell it, hey, I want to store this thing. I tell it where I want to store it in C for me. And then I can just close it up, right? And then when I'm ready to do it or to use it again, copy, paste. My recall is in the shift menu. I tell it to recall C, and then it brings it up on the screen again. right? Which is a really quick way that you could have, if you have three probabilities, three kind of big probabilities that you found, shouldn't say big, they're small, but large in number of numbers. Then you can say A plus B plus C, and then it'll just do it for you. Right? And so I like to use this shorthand just to remind myself where I stored stuff. Right? And then in your math, you can say recall C, recall A plus recall B plus recall C. If you've told me where you've stored stuff, I'm fine with that, right? Saving you a little bit of work. Okay. Oh, we did answer the question. I scratched out the pretty high, pretty low. If you were told the probability is 0.00055 of anything, or 4, I guess, you would say that probability is pretty low, right? And so there. But I think knowing the probability is more helpful. How would you know that it should be pretty low? In a group of 10, if the probability of being obese is only 26.2, what are you actually leveraging? You're expecting 26.2 out of these 10 to be obese, right? Now that expected value is a thing that we're going to work with. In fact, it's the mean. What? I know, right? It's crazy. So if you're expecting 2.62 out of these 10, right, and you get 8, that the probability of that, considering your expectation, is going to be pretty low, right? But we found the probability already to be very small. Oh. We even did the math, but I'll just highlight the right answer here. Should be this one, right? What's the problem with this one? Well, it doesn't incorporate the number of scenarios. 8 choose 10 is bad, and those two are bad in the next one, but we already did it, so I'm not too concerned. Bless you. Okay. So, any questions? Binomial probabilities. The birthday problem is a really famous problem where the probability of 2 people in a room, I can't remember how many people have to be in the room, where the probability of having the same birthday is actually quite high. And so we can calculate those. This is just for fun. I actually am not going to do it because we've got more important things to do, but you can watch a video on the birthday problem, and it's just kind of a fun binomial probability. I know, fun. I scratched this one out because I want to use the slide that's filled in. So in the previous example, we said, okay, the probability of 8 out of 10 being obese, if the probability is 26.2, should be pretty low, and we found that it was in fact pretty low. But like I said, what we were using was this expected value, right? How many expected successes would you have, right, in n trials? And so here, this is the expected number of successes in n trials with probability of success, P. Right? And that digs deep to the binomial being described fully by n and p. We don't need to worry about that, but the expected value is something that we use quite a bit. So here we had P was 0.262. And N was 100 in this case. So among a random sample of 100 Americans, how many would you expect to be obese, right? And so now we have this expectation that, well, 26.2% of 100 should be obese, right? Obviously, 26.2%, that doesn't exist, but this is the expectation, right? If you sample 100 Americans an infinite number of times, right? And so that's where it gets kind of boggy, right? But so the expected value is after an infinite number of times that you've run this trial. We know how to find this value, right? You would have just taken 100 times 0.262, right? And what we're going to find is that this expected value is the mean. What? Okay. The expected value is the mean, or is the mean. So we can denote it with a mu. Which means we have a mean for the binomial, which, okay, that feels weird, but it's there. Now, like I said, this doesn't mean that in every random sample of 100 people, exactly 26.2 will be obese. In fact, of course, that's not even possible. And so, but with, where does it, I think she says it later, so I won't do it now, but with repeated trials, we would expect 26.2. We can find the variation. What's the variation or the variability or the spread? Nice. All right. Sigma. The spread, I'll just put it here because I think you're ready for it, is, that's a square root, but it kind of got lost in the, of NPQ. Just as a fact. We're not going to talk about why that is, right? Just accept it as fact. Which means that we can calculate, if, as long as we know N and P, right? Which fully describe a binomial distribution, and this is the reason. Okay? As long as I know N and P, I can find the mean, and I can find the sigma, right? N and P again. Q is just 1 minus P, so I don't need any more information. Right? And I can take the square root of that, and I can find the standard deviation. In case you haven't felt it yet, we are gearing up to a z-score, right? With the normal distribution. We're not quite there yet, but we will. As long as we have a mu and a sigma, right, then usually we can calculate a z-score, right? Or we can always calculate a z-score. So the expected value is the mean. Okay. And the variability is, of course, the standard deviation. So we expected 26.2 out of 100 to be obese with a standard deviation of 4.4, right, once we do the math. Okay. Oh yeah, here it is. The mean and the standard deviation are usually not whole numbers, right? And that's all right. So just use the decimal version. I don't want you rounding these. Okay? And so this is what we would expect to see on average, right, upon infinite samples of 100. Oops. Right. Kind of hard to wrap your head around, so don't worry about it. As long as you're willing to accept it. Yeah, they sure are. So here, the mean, the variance, which we're not going to use, and the standard deviation of any binomial with n trials and p probability of success. Mu is n times p. The variance, sigma squared, is npq, but we use the standard deviation sigma, which is the square root of npq. So we use these two. Nice. Good. Oh, back in the formula sheet. We've established that any observation that's more than 2 standard deviations from the mean is considered unusual, right? And so what we can do is we can use that kind of rule or guideline to figure out a range for the plausible numbers of obese Americans in a random sample of 100, right? I expect 26.2 with a spread of 4.4, and I'm willing to go out 2 standard deviations, right? So this becomes mu plus minus 2 sigma, right, is what they've done. Plus minus, you go down a little, up a little from 26.2. And so sometimes I like to visualize it like this, where I have my 26.2 is my mu. And then I've gone up to, or sorry, down to sigma. Mu minus 2 sigma. And then I've gone up mu plus 2 sigma. In this case, this is 17.4 and 35.0, according to their numbers. So now I have this plausible range, right? Considering the spread and anything that happens, or if I take a random sample of 100 Americans and I find that anything between 17.4 up to 35 being obese, I would say, okay, I would expect that. That's not unusual to me. Okay. Out here, though, I would consider this an unusual observation, right? Same thing. On the other end, right? That's when we kind of start to say, oh, well, I don't know. I think the probability of those unusual things is pretty low, right? Nice. Can I just see, okay, we're doing okay. I know, doesn't feel like it. We should do this one. Okay. We've got a Gallup poll that suggests that 13% of Americans think homeschooling provides an excellent education for children. And they were given these categories: excellent, good, only fair, and poor. And we'll ignore this column here because we don't use it in this question. Now, would a random sample of 1,000 Americans where only 100 share this opinion be considered unusual? So, what do we have? We have share the opinion that homeschooling provides an excellent education, so they chose this category here. And so P, the probability of them picking that category is 0.13. That's what we're told. And what could you do? You could say, well, I'm going to lump these into not excellent. And all of a sudden, I have a Bernoulli trial or a binomial, right? I can only have a success failure. And if choosing excellent as a success, then I can lump them all into not excellent. And those are all failures. Right? I have a random sample of 1,000 Americans. Now I will highlight, kind of going back to our first week of classes here, when we say it's a random sample, what are we allowed to assume? We're allowed to assume that everyone in the sample, they're independent of each other. Right? It's just a random sample of 1,000 Americans. And so this allows us to, we can assume independence. That's why it's so important, because that was one of the conditions of the binomial working, right? Is that all of these individuals are independent of each other. N must be 1,000. One more zero. There's a decoy of 100, right? But we want to figure out, okay, if P is 0.13 and N is 1,000, then what is a plausible range? And then I want to see if 100 is inside or outside of that range. Okay. So I'll do this. I'm going to copy this. I'm going to give myself another page here. So we've defined a success as homeschooling provides an excellent education, which means that we were told that P is 0.13, and we already established that N is 1,000. I know, I want to clean that up, but I can't. From here, copy from your formula sheet. We're going to find the mean, right? How many would I expect? And then I need to know with what variability, right? And so I need to find the mean, which is N times P, which is 1,000 times 0.13. I'm expecting 130, right? But let me confirm here. Math is a morning subject. That's my excuse for this class, but actually I just don't do math in my head very well. I also need my sigma, my standard deviation. The square root of NPQ. I have N is 1,000 times P, which is 0.13, and Q, which is 1 minus 0.13. 0.87. Here, kind of a little cheater way. If you've just done the 130, you've already done the 1,000 times 0.13. So then you just need to multiply by 0.87 and take the square root. Just the tiniest of shortcuts, but still. I'm gonna pause at the square root 113.1. You don't want to forget that square root, right? Because it'll make a huge difference. But I get a spread or a standard deviation of 10.63484838, blah, blah, blah. A plausible range is plus minus 2 standard deviations. So mu plus minus 2 sigma is 130 plus minus 2 times 10.634848. Whatever. What's the harm in doing the last 3/8? I don't know. This is another scenario where you could use the store function, right? Bring it in. Or I can multiply what's on my screen. Fine, I'll keep going. By 2 first. 130 plus minus 21.269669675. I will store it in a and go 130 minus that guy. I get, so when we do an interval like this, I didn't even talk about it, I think. I forgot we haven't seen an interval like this. But what we do is we use round brackets, and then your lower value, comma, your upper value finished off with another round bracket. This is interval notation. So our lower value, 108.730332 up to 130 plus the recall A, I get 151.2696967. Although how did I? Oh, so from 130, you have to do them kind of individually. 130 plus 21 is 151. Oops. It gets confused. So a lot of people get confused by the plus and then the minus, but you list the minus part first and then the plus part. So here, this is the mu minus 2 sigma, and then this is the mu plus 2 sigma. So it's the lower, comma, the upper in round brackets. So I like to visualize it on a number line really quickly here. 108-ish to 151-ish. Just getting a quick idea. If I plot 100, which is the value we were interested in, right? So where only 100 share this opinion, be considered unusual, I would expect anywhere between 108 and 151. So 100 would be considered unusual. I'll say since 100 is outside the interval of plausible values, it would be considered unusual. Right? Anything outside this area would be unusual, and this area would be unusual. Now, probably the coolest tie-up in this chapter, I'll say, is that the binomial turns into a normal distribution. As long as your n is big enough. And so what that means is as long as our n is large enough, then we can use the normal distribution to find probabilities, right? And that's where we get the normal approximation to the binomial from, which is the bonus question on your test, is the normal approximation to the binomial, because this always happens. So I want to reward you if you kind of get through it on your own. I'll do my best, but it's not an actual question. So here, this is the bonus on test 1. So at n equals 10, the binomial distribution would look like this. N equals 30, it's starting to look like a normal. At n equals 100, it looks even more like a normal. At n equals 300, it definitely looks like a normal distribution, right? And so here, as n increases, the binomial becomes normal. How can we figure out, well, at what point can I go ahead and use the normal distribution to find probabilities instead of doing them all individually, right? That's the goal. How large is large enough? This is also called the conditions for the normal approximation. To the binomial. So the bonus question will say, you may use the normal approximation to the binomial if you've checked the conditions are true, right? And so what I mean by that is you have to check this. So the sample size is considered large enough if the expected number of successes and failures are both at least 10. Now you know how to find the expected number of successes, right? That's your mu, right? And so here, the expected number of successes, which is mu, which is n times p. So you have to check that n times p has to be greater than or equal to 10. And the expected number of failures has to be at least 10. Which means the smallest possible sample size that you could have with a p of 0.5 is 20, right? Smallest possible. As the p changes, you have to adjust your n. And so here, this is the expected number of failures. It has to be greater than or equal to 10. So in this case, if I only have 10 Americans, I guess, where did that come from? I don't know. Let's go to this one instead, because I don't know where that 10 came from. It's different. If we have the binomial distribution parameters n and p, which distribution can be approximated by the normal approximation or the normal distribution? So here we need to check that n times p has to be greater than or equal to 10, and n times q has to be greater than or equal to 10. N times p is 100 times 0.95, so I'm going to go with 95, which is greater than or equal to 10. So that one would be good, but what do I suspect? Well, if I'm expecting 95 successes out of 100, then I only get 5 failures, which is not greater than or equal to 10. So it's not an option, right? If n times p is 25 times 0.45. I get 11.25. That is bigger than 10, just barely. It still counts. It's okay. If I move on to n times q, which is 25 times 0.55, 25 times 0.55, I get 13.75, which is greater than or equal to 10. So that one would work. 150 times 0.05, I only get 7.5, so that one's bad. And if I have 500 times 0.015, I still only get 7.5, so that one's bad. So even though, notice, I have a sample of 500 trials, when I'm trying to pick up on something very, very rare, I need even more, right? And so for these, for very rare outcomes, we need very large samples, which makes sense. If you're trying to detect something really, really rare, a rare disease, for example, then you wouldn't just go out and collect a sample of 100 and say, oh, I didn't find any. Right? Well, were you expecting to find any? No. Right? Well, then you got to keep going. Right? And so these I would consider rare outcomes. Fine. I'm going to skip this one. So it's about Facebook users. I know I am out of time. I've got 1 more minute. Okay. 25% of Facebook users are considered power users, which we talked on the earlier slide, but I skipped it. And the average Facebook user has 245 friends. What's the probability that the average Facebook user with 245 friends has 70 or more friends who would be considered power users? Uh-oh. We've got a probability of success P, 0.25. I have some number of trials, 245. N is 245. And I want to know if K is 70 or more. Uh-oh. That would be the probability that K is 70 or 71 or 72 or 73, all the way up to 245. I really, really don't want to do that, right? Like really, really don't. You'd use Excel for it, okay? But at this point, I think even Excel does use the normal approximation to the binomial. And so what it does is it says, well, if Z is X minus mu over sigma, X would be our 70 that we're interested in, finding the probability of 70 or more gives us this area. That's the area that I'm interested in. Okay. So 70 minus the mean, 61.25, which they've calculated for us, divided by the standard deviation, 6.78. As long as you've checked the conditions, n times p, n times q both have to be greater than or equal to 10, you're allowed to use the z. Now from z, we know how to use the z table to find this area. Okay? So I'll leave it with you. Yes, question before I do that.
It's not going to the left. That said, couldn't do that.
Do you mean here?
Yeah.
The Z table only gives you the area to the left, but you can use the 1 minus to find the area to the right. Cause the total area is 1. Sold. All right,
Believe you. You know.
that's a good policy.